5.6 continues talking about operations with radicals. Now, radicals behave just like variables. So let's take a little sidebar for a minute. And if we have 2x plus 3y, we know we can't combine that because this x and this y are not the same values. But if we have 2x plus 3x, we know we can combine that to make 5x. This is exactly what radicals do. If I have 2 radical 3 plus 3 radical 5, I can't combine that. That's done, just like I was done with the variables. Addition and subtraction are very picky. This is saying I have 2 radical 3 things plus 3 radical 5 things, and those two can't be combined. But in this one, if I had 2 radical 3 things plus 3 radical 3 things, I really have 5 radical 3 things. So if you are worried or you get confused, radicals behave just like variables. So in the earlier ones where we had the square root of 2 times the square root of x, well, if we had x times y in a problem, we would write xy. We can do the same thing here. So the rules for combining, when you combine, what operations you can do for radicals, for the most part, are the same as variables. So if you get confused, stick in a variable, see what you could do, then go back to your radicals. It's likely the same. So that being said, we have to always simplify first. So you need to reduce all of your radicals and then combine like terms. Combine like terms. So we have to look, perfect squares, looking for perfect squares. So this is 9 times 5. I'm going to factor everything. Now when you factor 80, you could start with 2 times 40. We're looking for perfect squares though. So I know 4 goes into 80 20 times. There's a perfect square. I know 4 goes into 20. And 20 is 4 times 5. So I'm going to rewrite everything first. So I have 3 times the square root of 9 times 5. I haven't changed anything. I am just writing it as prime factors with, well, not even prime factors. I'm writing it as the factors with perfect squares so that I can simplify. Now, if you wanted to go all the way down to 2's, you certainly can. You just make yourself a little bit more multiplication. So I'm going to simplify first. So I can take, I've got my 3 here. The square root of 9 is 3. Can't take the square root of 5, so it stays out. This 5 comes from right here. The square root of 4 squared is 4. Can't take the square root of 5, so it stays under the radical. This 4 stays out here. The square root of 4 is 2. Can't do anything with the square root of 5. Do the multiplications out front. I have 9 square roots of 5 minus 20 square roots of 5 plus 8 square roots of 5. Now, since all of these are square roots of 5, I can combine them. It would be just like this would say 9x minus 20x plus 8x. We could go ahead and add those all together. When I do that, I end up with negative 3 square roots of 5. Remember, this is just think as an example. And so that is your final answer. Cube rooting works exactly the same way, except instead of looking for perfect squares, we're looking for perfect cubes. So 54, I'm not going to worry about the cube thing. I know the factors of 54 are 6 and 9. I know that's 3 and 2. And I know that's 3 and 3. If you're unsure about the perfect cube, the perfect fourth root, just factor it all the way down and rewrite it as powers, and then you will see your factors. 16, let's see, that's 2 times 8. 8 is 4 times, 4 times 2. This is 2 times 2. And notice I'm circling the ends. And if you remember prime factor trees, that's a nice way so you don't lose track of things. So what do I really have here? I have the cube root of 2 times 3 cubed minus the cube root of 1, 2, 3, 4, 2, well, I want groups of 3, so I'm going to rewrite it right away like that. I still have 4, but I know I'm looking for groups of 3. So my simplifying step, the cube root of 2 cubed, can't do anything with that. The cube root of 3 cubed is 3, so that one comes out front. Minus the cube root of 2 cubed, I can do that. That's 2. Can I take the cube root of 2? Nope, that's left over. Then I check, do I have the exact same radical? Yes, so I can combine these. 3 cube roots of 2 minus 2 cube roots of 2 means I have 1 cube root of 2. And just like with variables, you could write the 1 here or not. It doesn't matter. Most of the time you will see it not in there. And so this is your final answer. Multiplication is going to, again, work just like if you have variables. This is 2 binomials, so we're going to go ahead and FOIL. So we take first 2 terms. Now, constant times constant, radical times radical if it exists. So in this case, I have 6 radical 3 for my first term. Outside terms, there is no constant except the negative 1 plus negative 2 square roots of 3 squared. Radical 3 times radical 3. You could also write radical 9. It's up to you. Inside terms, the 3 times the 3 plus 9 square roots of 5. Last 2 terms plus negative 3 square root of 15. You have 4 terms. Now I have to simplify and clean up my radicals and combine. Now when we FOIL regular binomials, we usually boil down to 3, the outside and the inside combine. That's not always going to happen when you're using radicals, because remember, those radicals have to be identical. So 6 radical 3 can't be changed, plus negative 2. Now the square root of 3 squared is 3, plus 9 radical 5 can't be changed. And radical 15 can't be changed because there are no perfect square factors. Clean this up. 6 radical 3 minus 6 plus 9 square roots of 15 minus 3 square roots of 15. And because none of my radicals are the same, I have a 15. Oops. None of them are the same when you write your problems, right? None of them are the same. I'll fix that in a minute. I can't combine anything. So that is my answer. Now we're going to go ahead and do the same thing over here. We're going to FOIL. So first 2 terms times each other. Constants times constants. Radical times radical. Outside terms. Minus 7 times 4 is 28, square roots of 2. Inside terms, plus 7 times 4 is 28, square roots of 2. Last 2 terms, minus 49. These 2 are identical, so I can combine them, and I can simplify that one. So I have 16 times 2, that becomes 0, minus 49, 32 minus 49 minus 17. And that's your answer. So sometimes your radicals will disappear entirely depending on the combination that you have. Now, here we need to talk more about rationalizing the denominator. Conjugate is a new definition piece, and so let's take a little sidebar. So just to review, when we rationalize, up until now, we've had products. We've had things like 3 over the square root of x, so then we multiplied top and bottom by the square root of x over the square root of x to make 3x over 3 square root of x over x, because we wanted to get the radical out here, because this made the square root of x squared. Well, things are going to change. When we have something like 3 over the square root of x minus 2, now it's not so easy to know what we should multiply that by to get it out of the denominator. So in keeping with the idea of needing perfect squares, this example really isn't that different from this one, because I need this exact thing. So I'm really going to multiply top and bottom by that exact expression again. So that means there are 2 of them, so this is really the x minus 2, the quantity squared. So in the numerator, I'll have the square root of x minus 2 all over x minus 2. Still the same process. Now, where it changes, though, is when I have something like this, 5 over 3 minus the square root of x. Now, if I just tried to multiply this top and bottom by the square root of x, this is a single number. I would have to do the distributive property, and I would end up with 5 square roots of x over 3 square roots of x minus x. And I haven't gotten anywhere because I still have a radical. And so this is where the idea of conjugates come into play. And conjugates is a way to make that perfect square binomial, that a squared minus b squared kind of idea. So if you're faced with something like 3 minus 5 over 3 minus the square root of x, what you need to multiply top and bottom by is 3 plus the square root of x, single number, 3 plus the square root of x. Because if you remember, this factors into this. Squaring will get rid of my radical, but there's no AB term. The middle drops out because it's 0. So then, when I work this, I have distributive property in the top, so 15 plus 5 radical x all over, FOIL the bottom. 3 times 3 is 9, minus outside 3 square roots of x, inside plus 3 square roots of x minus last square root of x times the square root of x. These two are going to disappear, and so I'm going to end up with 15 plus 5 square roots of x all over 9 minus square root of x times the square root of x is the square root of x squared, 9 minus x. And that is your final answer. I'm going to go back to the lesson in part 3 of the video.